Explain the concept of linear regression. Linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. The goal is to find the best linear relationship between the variables, which can be used to make predictions or understand the nature of the relationship between the variables. In a simple linear regression model, there is only one independent variable and the relationship is modeled using a straight line equation in the form of y equals mx plus b, where y is the dependent variable, x is the independent variable, m is the slope of the line, and b is the intercept. The slope m represents the rate of change of y with respect to x and the intercept b represents the value of y when x is 0. In multiple linear regression models, there are more than one independent variables and the relationship is modeled using the linear equation in the form of y equals b0 plus b1x1 plus b2x2 plus bxn, where y is the dependent variable, x1 x2 xn are the independent variables and b0 b1 b2 bn are the regression coefficients. The linear regression model can be used to make predictions of the dependent variable for new values of the independent variables. The model is trained using a data set with known values of the dependent and independent variables, and the coefficients are estimated using a method such as least squares regression. The model's accuracy can be evaluated using metrics such as mean squared error or R-squared, which measure the goodness of fit between the predicted and actual values. What are the assumptions of linear regression? Linear regression relies on a set of assumptions about the nature of the data, the model, and the error terms. The following are some of the most important assumptions of linear regression. Linearity. The relationship between the dependent and independent variables should be linear, which means that the change in the dependent variable should be proportional to the change in the independent variable. Independence of errors. The errors or residuals should be independent of each other, which means that the value of one error should not influence the value of another. Homoscedasticity. The variance of the errors should be constant across all values of the independent variables, which means that the spread of the residual should not change as the independent variable changes. Normality. The errors should be normally distributed, which means that the distribution of the residuals should be symmetrical around 0. No multicollinearity. The independent variables should be uncorrelated with each other, which means that there should not be any perfect linear relationships between the independent variables. These assumptions are important because they affect the accuracy of the regression model's predictions and the reliability of the statistical inferences made from the model. Violations of these assumptions can result in biased and inefficient parameter estimates, incorrect confidence intervals, and inaccurate predictions. Therefore, it is essential to check these assumptions before using linear regression and take appropriate corrective measures if necessary. How do you evaluate a linear regression model? There are several methods for evaluating the performance of a linear regression model, depending on the specific goals of the analysis. The following are some of the most common evaluation metrics used for linear regression. Mean squared error MSE. This is a measure of the average squared difference between the predicted and actual values of the dependent variable. A lower MSE indicates better performance of the model. R-squared. This is a measure of how well the regression line fits the data, representing the proportion of the variance in the dependent variable that is explained by the independent variables. An R-squared value of 1 indicates a perfect fit, while a value of 0 indicates that the model does not explain any of the variability in the dependent variable. Adjusted R-squared. This is a modification of the R-squared value that adjusts for the number of independent variables in the model, penalizing the inclusion of unnecessary variables. Root mean squared error RMSA. This is the square root of the mean squared error and represents the average difference between the predicted and actual values in the original units of the dependent variable. Residual plots. These plots are used to visualize the distribution of the residuals and to check for violations of the assumptions of linear regression, such as heteroscedasticity or nonlinearity. In addition to these metrics, it is also important to consider the practical significance of the regression coefficients and to check for potential issues such as multicollinearity or influential observations that can affect the reliability of the model. What is multicollinearity and how does it affect linear regression? Multicollinearity is a situation in which two or more independent variables in a linear regression model are highly correlated with each other. In other words, multicollinearity occurs when there is a strong linear relationship between two or more independent variables, making it difficult to distinguish the individual effects of each variable on the dependent variable. Multicollinearity can affect the accuracy and reliability of a linear regression model in several ways. 1. Unreliable estimates of regression coefficients. Multicollinearity can cause the regression coefficients to be unstable and unreliable because the model cannot distinguish the individual effects of the correlated variables. This can result in large standard errors, low t-statistics, and insignificant p-values for some of the variables. 2. Misleading interpretation of regression coefficients. When two or more independent variables are highly correlated, their regression coefficients can have opposite signs than what is expected based on their individual effects. This can lead to a misleading interpretation of the coefficients and the direction of the relationship between the independent and dependent variables. 3. Reduced predictive power. Multicollinearity can reduce the predictive power of the model because the model may be overfitting the data, meaning that it is too closely fitted to the sample data and may not generalize well to new data. How do you select variables for a linear regression model? In linear regression, the goal is to build a model that can predict the value of a dependent variable based on the values of one or more independent variables. Here are some steps to follow when selecting variables for a linear regression model. 1. Define the problem and the question you want to answer. Determine what you want to predict and what factors may influence the outcome. 2. Gather the data. Collect data on the dependent variable and potential independent variables. 3. Examine the data for patterns and relationships. Plotting the data can help you see if there is a linear relationship between the dependent variable and each independent variable. 4. Calculate correlation coefficients. Calculate the correlation coefficient between the dependent variable and each independent variable. Variables with high correlation coefficients are more likely to be good predictors. 5. Consider the practical significance of the variables. Even if a variable has a high correlation coefficient, it may not be a practical predictor if it is difficult to measure or if it is not related to the problem you are trying to solve. 6. Use statistical methods to determine variable importance. There are various statistical methods for selecting variables in a linear regression model, including stepwise regression, forward selection, and backward elimination. These methods can help you determine which variables are the most important for predicting the dependent variable. 7. Validate the model. Once you have selected the variables for your linear regression model, you should validate the model to ensure that it is accurate and reliable. This can be done by using the model to predict the dependent variable for new data and comparing the predicted values to the actual values.